Here we're going to learn 4 basic patterns of electron flow. And what's nice about this is once you have a handle on these 4 patterns, you're going to be able to apply them to pretty much any reaction we study and break down the reactions into a set of these different patterns. So we're going to start with nucleophilic attack, and really this should be pretty familiar because this is kind of what we've been talking about as we began this chapter. Say you're given the bromide ion and a carbocation. So we know the bromide actually has 4 lone pairs. And one of those lone pairs I'll highlight in red so we can keep track of it. That's going to be our nucleophile. And then the carbocation carbon, that's electron deficient, so that will be our electrophile. And what you want to do, as we've done before, put your pencil down on the nucleophilic lone pair. Draw a curved arrow to the carbon that bears the positive charge. That's a nucleophilic attack. Or you can think of it as the nucleophile's electrons attacking the electrophile. When we draw the product, here's our electrophile, and then I'm going to add a new bond to that electrophilic carbon, and that has the bromine attached. And there's the product. So the new bond here was made from the lone pair on the bromide. When you're doing reactions, check your charge balance. If you look on the left side, you have something that's negative, something that's positive. So a net 0 charge. If you look on the right side, you have something that's neutral, net 0. Make sure your charge balance is maintained in each step. Here's another example. We have these 2 species here reacting together. And like acids and bases, where sometimes something will act as an acid, and in another case that same thing will act as a base, nucleophiles and electrophiles can be a little bit similar. Like in the case of this ketone here, the oxygen has lone pairs that could potentially act as a nucleophile, but we also know the carbon that's part of that double bond is an electrophile. But in the case of the amine, it really isn't electrophilic, so it becomes kind of the de facto nucleophile. So that's how we can figure out which is which. So we have our nucleophile and our electrophile. And just like before, put your pencil down on the lone pair, draw a curved arrow to the electrophilic atom. Now what we see here is this carbon already has 4 bonds. It can't have 5 bonds. So what that means is an electron pair needs to be pushed away from that carbon. And what we can push away is the pi bond. So I'm going to highlight one of the pi bonds here in green. And what I'll do is send that away from the carbon and onto the oxygen as a new lone pair. So an electron pair must be pushed away, and that's what we did there. Right, so to draw our product, you could potentially draw the nucleophile or the electrophile first. I'm just going to draw kind of the electrophilic portion, and then we'll attach the nucleophile. So this oxygen already had 2 lone pairs, and we gave it a third in the course of the reaction. The electrophilic carbon has a new bond from that red lone pair, and I'll draw that new bond in red. And that is attached to the nitrogen, the NH2. Right, and that nitrogen still has the 3 carbons attached. Just like that. When you're done, check for formal charges. So your oxygen now has an unusual number of bonds. So if you calculate its formal charge, it's -1. The nitrogen has an unusual number of bonds. If you calculate its formal charge, it's +1. Again, we've maintained charge balance. Net zero on the left, positive and negative means net zero on the right.